pleasure to, oh, okay, I'll start now. It's a very great pleasure to introduce Alexander Itz, who's going to talk about global asymptotic analysis of the Painleve equations.
Thank you very much. Thank you very much, organize. Thank you, Eddie. Thank you, for you and for Ines for giving me this opportunity. Yes, it is. Well, it is. I am sort of excited because I'm not going to talk about resurgent and trans-series. Maybe it's the very end. So the whole idea of my taking part on this program was to learn these things. Unfortunately, it is not. Yes, a kind of online version is not very good for learning. But nevertheless, I would think that I would try my best to present what another story. So it is sort of the way how to approach asymptotic analysis using the different ideas. It is they are narrow in the sense that they are applicable only to integrable situation, to Painleve. But I believe it is very useful. It would be relevant to try to look at it and maybe even to try to understand them from what sort of the relation links can be made between what I call Isomonodromy-Riemann-Hilbert approach and trans-series resurgent analysis. So I'm going to present mostly old results. They are some of them already forgotten, in fact. So I think again it is my another excitement, that the opportunity to sort of to highlight some past results, which I believe still relevant and would be good to kind of comprehend from this. A little bit of history. So I will start from the history again. The history, it's as every history presentation it's going to be incomplete and maybe biased. But the main point is this is, of course, part of the history. I am going to talk in detail about the development of Isomonodromy-Riemann-Hilbert method. So the story begins from these two seminal works in 1980, when it was a sort of rediscovered the lax integrability of Painleve equations. Rediscovered because it was known, although not as in the name of lax integrability, by the classical people, by the Fuchs, Garnier. But I will start with the new history, with the works of. So I would mark the beginning of what I am calling in Isomonodromy-Riemann-Hilbert method. I mark it by the works of Jimbo Miwa-Una, where they come up with the lax representation through the monodromy theory of linear systems, and Flaschke-Newell, who discovered lax representation for Painleve through the self-similar reduction of integrable PDEs. So these observations led to what indeed to Riemann-Hilbert Isomonodromy method of studying Painleve equations. There are two directions, two directions in this method. I want two branches. One, it is just to use Riemann-Hilbert representation for Painleve equations to prove existence of solution global properties, Painleve properties, using facts about Riemann-Hilbert problem. So this is the important difference with the classical works. So in classical works, it was discovered this isomonodromy nature of Painleve equations, but the reformulation of this connection as through the Riemann-Hilbert problems was not done because there was no Riemann-Hilbert problems at the beginning. So it was only during the Plimel's works when it was Hilbert 21st problem was reformulated as a analytical factorization problem. So in our time, we already had this advantage of having the powerful analytical apparatus of Riemann-Hilbert problem, and so this Riemann-Hilbert representation of Painleve equations allowed to study the initial value problems in the sense of existence, meromorphicity, and also in some cases, important cases, but not in all, global existence, the smoothness. I'm not going to talk much about this part. This is the main references. I'm going to talk about the second direction which method took. It is its use to asymptotic analysis. And this again, I would indicate another two branches, another two ways to do it. First, and it was historically first, it was to use direct monodromy problem approach. So there is this correspondence between Painleve equations and monodromy data. So monodromy data, you in direct monodromy problem approach, you assuming something about your solutions, you try to solve asymptotically direct monodromy problem, calculate Stokes matrices asymptotically. Then they are integrals, and so you can get asymptotics information about your solutions in terms of monodromy data. So this is was first. So this is a kind of the this is the basic works. I believe it was first it was done in 1982 by Jimbo for Painleve 6, by Novakshonov for Painleve 3, and by myself and Petrov, my then graduate student for Painleve 3 also. So then it was developed by many other peoples, and I call all this as a complex WKB method. So here we have to use some WKB approximation for solution of linear systems in complex domain. Also, of course, the similar things was done a little bit, started a little bit later, and then continues by now. By the first it was done by Takei and Kawai, and this is now called exact WKB method. I never analyze carefully what is the relation between those two. It should have been done, in fact. So, but there is one maybe superficial difference, that here you use the Schrödinger type, the scalar complex WKB to the scalar Schrödinger equations. Here we are doing the systems. Okay, so this is one approach. So it can be said that it is the main idea is to use asymptotic solution of the direct monodromy problem. The second, another line of using this Riemann-Hilbert representation for Painleve equation, it is a use inverse monodromy problem approach. So now you are not assuming nothing about the solution a priori, and you just try to analyze, to try to solve asymptotically the corresponding Riemann-Hilbert problem. As a precursor to this inverse monodromy problem approach, I would call these two works. It is a Hastings-MacLeod in 1980 and Clarkson and MacLeod in 1988. So this is a famous Hastings-MacLeod solution. They analyze it and prove connection formula for it. And Clarkson and MacLeod, they analyze so-called Ablovitz-Sigur family. And they use kind of the inverse monodromy problem approach in the form of the reverse scattering method. So it took some kind of the marching equations. And then in 1992, it was come up this David Zoom nonlinear steepest descent method, when you start from the Riemann-Hilbert problem. When you start not from the kind of the Fourier transform of the corresponding singular equation, but from the Riemann-Hilbert problem itself. And you, just like in the usual, in the classical steepest descent, when you have contour integral, you deform your contours, trying to come to the Riemann-Hilbert problem whose jump matrices asymptotically approach identity. And in the way of this deformation, you go through several model problems, which can be solved explicitly in terms of the hypergeometric special functions or elliptic special functions, or simply the degenerating elliptic special function. So this is the essence of the nonlinear steepest descent method. And this reformulation of the inverse monodromy problem approach proved to be very useful, not only for Painleve equation, for ODE and PDE, but also it proved to be very convenient to apply to some other areas. So this is why this method went beyond the Painleve equations. So it is orthogonal polynomials, random matrices, Stokes determinants, random processes. So that was a really important development. Okay, so this is, again, it is not the whole history, but I just want to just summarize this part of the history. That first we have realization of the monodromy, isomonodromy meaning of Painleve equations. This allows us to present them, to develop what we call the Riemann-Hilbert representation for Painleve equations. In modern time, it is called, people very often use Riemann-Hilbert correspondence. I deliberately don't use it. I deliberately use Riemann-Hilbert representation because we use this to solve Painleve equations. So this is just like contour integral representation. You are not saying about contour integral correspondence when you are solving some equations by contour integrals. You are talking about contour integral representation. The same, I use this term as the Riemann-Hilbert representation, because especially in the form of nonlinear steepest descent, it is very close indeed to the, sometimes we even use the term non-abelian contour integral representation. So you can actually treat, you can actually consider, you can actually treat the Riemann-Hilbert representation, Riemann-Hilbert problems, matrix Riemann-Hilbert problems as non-commutative contour integrals. Okay, I conclude this short history description by just saying what, on my taste, are very important recent advances in inverse isomonodromy-Riemann-Hilbert method. They are, first of all, related with the discovery of the connection between Painleve and conformal field theories. So this is this Ukrainian group, Kiev, so-called Kiev formula, Ukrainian group of Gamayan, Yegorov, these people, who found indeed the very remarkable representation of tau functions with Painleve equation as a form of some conformal block Fourier type series, which actually allows to solve long-standing problems of calculating the constant in the asymptotics of tau functions. Also, it led to the kind of another development, continuous development of this was the very, very convenient Fredholm determinant representation for tau function. So this I consider as a very important development. It's still going on. There is a lot of things to be done, but in my point of view, kind of after Jim Bami with Una, it is a next conceptual development. It is a next conceptual development. And I want to, so it is going on now, and I want to just emphasize one of the very last works by Iwaki, when this conformal block type series was produced for asymptotics in complex domains. So far it was only for this kind of nonlinear Stokes race, trigonometric asymptotics, but this is for complex domains. That is, so maybe I will have time, but probably I won't have time to talk a little bit more about it. Okay, no, the very end of my introduction is, of course, I should mention these non-isomonodromy schemes. I'm not going to talk about them, but in a sense, it would be, of course, very important to try to make bridges. So non-isomonodromy schemes, it is, of course, first of all, should be mentioned these works of the Nalini and Martin Kruskal. So when they applied use just Painleve property and multi-scale asymptotic analysis. So they realized that you can apply, you can actually separate fast and slow variable in the Boutroux I will talk about it later on, but what I'm saying is that this is a very first rigorous works on the asymptotics of Painleve by non-isomonodromy techniques. And of course, this is exponential asymptotics, trans-series, resurgence. This is what is going on now in institute, I believe. So this is and again, I repeat, it would be so. This would be so important, on my view, to make bridge between those two cultures. So this is exponential asymptotic, trans-series, resurgent, and isomonodromy technique. So this is what I kind of that was one of my major reason to try to join the program. But since I cannot do it in person, it's disappointing. Okay, so that is, but again, maybe in the end, how much? I will. So there are actually now there are very good indications that these relations can be established, and in fact, I believe that there are already some talks in the program. Okay, so what now I'm going to talk just about indeed Isomonodromy-Riemann-Hilbert method. What can be achieved by this method? So complete description of all possible types of asymptotic behavior of the Painleve transcendents at the relevant critical points. So it is explicit connection formulas, distributions of poles, and quasi-linear and nonlinear Stokes phenomena. So this is some of the major issues of the global asymptotic analysis, of course. So this has been done for almost all Painleve equations by now. Not all, unfortunately, most of this was done by Andrei Kapaev, but he passed away, and not many of those. There are many parts of it which are not published, which is done but not published. So, but anyway, so it is in principle it is doable for all equations. It is definitely published and done for Painleve 1, for Painleve 2, for Painleve 3. Many paths for Painleve 4, for Painleve 6, everything is done, but not. So it is basically it is fair to say that almost everything is published now from these sites. So I will illustrate these results. So first of all, my plan is to illustrate these results, and if time permit, to say a few words on how they are obtained. And I will consider Painleve 2 as a case study. Painleve 2 without constant, so the simplest Painleve equations, the simplest for analysis. Okay, first we start from the Riemann-Hilbert representation of the solution of Painleve 2. So they can be marked, they can be identified with the following monodromy manifold. I believe that it was already, you might saw it already in the nonlinear Stokes. So this cubic algebraic manifold, without singularities, by the way, is described the whole set of Painleve equations. So now I'm going to remind or show how you associate with every point of this manifold a Painleve function. So first of all, you take the point, you take the point, why it becomes so big? Yes, you take the point S is this, and you construct three, well, of course, Stokes matrices. You construct those three Stokes matrices. These relations, by the way, is equivalent to this cyclic equation. So all odd matrices are low triangular, or all even are upper triangular. And then you organize the Riemann-Hilbert data. So it is a contour, which is just 6 rays. And for each ray, I associate my Stokes matrix S, and the jump matrix on each ray is this, the corresponding, the relevant S with this similarity transformation, which is dressed by these exponential functions. So this is the data, Riemann-Hilbert data. Now, having Riemann-Hilbert data, we formulate the Riemann-Hilbert problem. So to find a 2x2 function y, which is analytic outside of the gamma, which has plus minus boundary values on the gamma and are related by matrix G. So in each ray, you have a relation with this matrix G. And at infinity, we demand that it goes to identity. First of all, I want to notice that the problem is well posed. In which sense? So because of this special triangularity of these matrices, this G is always approach identity exponentially fast as lambda goes to identity along the ray. So this is exactly the triangularity as it should be to guarantee this asymptotic behavior. And now the cyclic relation guarantees that you can define your plus minus value in a very classical way. So your y, if you restrict your y on this sector, is going to be just continuous in the closure of the sector. So this is the problem is very well posed in this sense. And there is a theorem, which in fact was proven only relative in 2004. It is Bulibrook, myself, and Kapaev, that for every S, there exists meromorphic in X solution. So what does it mean? Well, I don't want to put too many details. Meromorphic in X means that for every S from monodromy manifold, there is a discrete set of X's, complex X's, accumulating only to infinity, such that outside of this set, we have a solvability, and the independence on X is also analytic, and those set is just the poles of function Y. Now, the theorem 2, if you define U of X according to this relation, so it would depend on X, then it is meromorphic because of this, and it satisfies Painleve 2. Moreover, every solution of Painleve 2 admits this Riemann-Hilbert representation. This is what I call Riemann-Hilbert representation for suitable S. So this should be attributed just to the Flash-Canuel paper 1980. So what are the corollaries of these statements? First of all, it means that I can, is it too small? Is it okay? Is this size?
Yeah, we can see.
Huh?
We can see.
Yeah, it's a good size. It's a good size.
Okay, good. So the first corollary is that I just take those S's, this point of the manifold, as a parameterization of Painleve functions. So just to use this notation. And secondly, of course, that Painleve 2 possesses Painleve Pro. This is, of course, there are many other proofs, but this is also corollary of this theorem. Now, just to mention what is the relation of this Riemann-Hilbert problem to isomonodromic, to the monodromy theory. So why we talk about isomonodromy theory? Okay, so let us go from Y to psi. So let us incorporate this exponent which participate in definition of the jump matrix into function Y. Then for psi, in psi, the Riemann-Hilbert problem will be written in this way. So now the jumps are just constant S's. But at infinity, of course, there is a price. You would have essential singularity at infinity. Immediately from this, it follows, it is everybody knows, of course, this sort of arguments, that if I consider logarithmic derivatives of psi, because S is constant in lambda and in X, we will get just polynomial derivatives. So this is going to be the second, this is the first. Or it means that the solution of my Riemann-Hilbert problem, the psi solution, satisfies the Lax pair, satisfies this two linear equations matrix. So this is a polynomial of the second degree, polynomial of the first degree. Coefficients matrices A1 and A0, U0 are given in terms of the expansion, which is the extra claim that we have the full around this kind of asymptotic expansion at infinity. You take M1, M2, and in these terms you get the coefficients of A1, A0, U0. In fact, everything depends just of two parameters, U and W. This is a off-diagonal element of the M1. This is a combination of off-diagonal and diagonal elements of M1 and M2. U and W. So you see our monodromy data are parameterized by basically two-dimensional manifold. And here we have two parameters, U and W. And this is a Flash-Cannuel Lax pair. So what we have here, it is a Flash-Cannuel Lax pair. So if I consider the compatibility condition, I get this zero curvature equation, which is equivalent to the Painleve 2. So W is just derivative of X, and U satisfies Painleve 2. Also, if I consider restrictions of psi on those sectors, then in terms of these restrictions, I get 6 psi k. Each of them behaves like that, are related by this relation. This is a Stokes relations. And so what we are doing, what we are dealing now here, it is just a canonical solution for this system, for this second order polynomial system, and Sk are just the Stokes matrices of this system. So that is the relation. And from this point of view, the Stokes parameters are first integrals of Painleve 2. So this is one of the very important way to see on this relation. So the Stokes parameters are, they provide us with a complete set of the first integrals. Of course, they are transcendental, but the direct monodromy problem approach in the asymptotic analysis, it is exactly to calculate the asymptotics of these parameters, assuming certain asymptotic behavior of U and Ux from equation. So this is the roadmap. You look at the equation, you see what is the reasonable assumptions about U and Ux. You plug it in, and you begin to the complex WKB analysis of this system, and you construct the asymptotics of the Stokes matrices. And this is how you get, and then you put them constant. This is how you get asymptotics with using the direct monodromy problem approach. For inverse monodromy problem approach, you look just at this Riemann-Hilbert problem, and as I said, try to deform the original contour to the contour when your matrix would be not only with respect to lambda approach identity, but with respect to T and uniform in lambda. Again, if I have, but probably I won't, time I can say more about this. Very well. So this is what this is all about the settings, the monodromy settings, the Riemann-Hilbert settings, the Riemann-Hilbert representation of Painleve functions and their relation to the monodromy problem and to the treating of the Stokes matrices of the relevant linear equations as the first integrals. Now, let me illustrate what can be done from this representation. Again, I would consider, let me just illustrate the first statement in my table, that the complete description and with all connection formulas. To this end, I consider sort of simplest case. So I consider pure imaginary solutions. Pure imaginary solutions. For pure imaginary solutions, it means that in form of the Stokes parameters, S3 should be related by this to S1, and from this relation we get formula for S2. So it means that we have just monodromy manifold, monodromy submanifold of this for the pure imaginary, it is just the whole C. No restrictions on S1. No restrictions on S1. Of course, it is the same to say that real for this equation, pure real for this equation. And of course, the simplification of this thing is that there is no poles on the real line. So the behavior, it is a simple fact. It is a simple fact. And now let me present you the one of the kind of the main theorem, which describes so this is the example. This is an example what can be done with the Isomonodromy-Riemann-Hilbert method about Painleve equations. So let's take any complex number S1 and consider the corresponding Painleve 2, pure imaginary. Then the claim is that when x goes to minus infinity, we have this sort of ARA functions behavior. Yes, so it looks like ARA functions, amplitude alpha, phase phi, but we have to have this logarithmic shift, which is understandable because of the U cube. So of course, to predict and even prove that there is this collection, there is this type of solution of Painleve 2 is not very trivial, but it is not very difficult thing. What is of course important is that I connect explicitly this alpha and phi with S1, with my monodromy data. This is a formula. So this is a formula for alpha. This is a formula for phi. So it involves no more than gamma functions. No more than gamma functions. It is at minus infinity. So at minus infinity, you can say that every solution behaves, in particular, we claim that every solution behaves like that. Now, what is going on plus infinity? There are two types. Generic, if imaginary part of S1 is not zero, then I have this square root growing behavior. This is a background, square root background, and again, oscillatory type of asymptotics. Now it is the frequency is very different, 2 square root. So there is no, in linear situations, there is no this type of solution, of course. And again, the parameters are rho and theta. And so for rho and theta, again, I have formulas in terms of S1, in terms of the same S1. Again, elementary formulas. The maximum is gamma function. But again, this part is going to be very easy as soon as rho squared is found. It is already known. The same as here. As soon as alpha squared is determined in S1, this part is determined. So this is generic behavior. And if imaginary part of S1 is zero, I have behavior just like for ARA function and plus infinity. And this is amplitude, it is S1, it is here. S1, it is here. So this is the graphs, what is going on, generic and this thing. And what I want to say is that this is now what I can say, in fact, I can exclude S1 from this and get statement about asymptotic behavior completely in intrinsic terms. So let me just show it to you. It is some kind of prepared in the other slide. In the other slide. Do you see it?
Yes. Yes.
Yeah. So now I just reformulate the same statement, what I did, but in intrinsic terms. So what we claim that every pure imaginary solution for real x of Painleve 2 behaves like this, where alpha and phi are parameters at minus infinity. And they can be taken as initial data. They can be taken as the parameters of the solution. Then what is going on in plus infinity? Let's make the following combination of alpha and phi. Let's call it delta. If delta is not zero modulo pi, then at plus infinity, I have this behavior. and the amplitude and new amplitude and new phase are related in terms of alpha and phi according to these explicit formulas. According to these explicit formulas. So again, it is elementary formulas. The maximum transcendentality is gamma function. If it is 0 modulo pi, then we have this is Ablovis-Sigur behavior. And again, the relation between rho and alpha. So this is an example of, as I said, complete description and connection formula. So everything now in this formulation intrinsic. And you see, it is these connection formulas are no worse in the sense of the, again, efficiency than the connection formulas for the classical special functions, for Bessel functions, parabolic cylinder functions. Again, no more than gamma functions. Gamma functions are involved there too. But there is an interesting point. For Painleve, we don't, for classical special functions, we have contour integral representation. So it is not surprising that we will get connection formulas in terms of contour integrals, gamma functions. Here, we don't have contour integral representation for the Painleve, but connection formulas are of the same efficiency as for classical. So I am going back to my main. Yes, I'm going back to my main, but I have to again to share it. Yeah. So we're now back to. I just want to make. Okay, so this is what is good. One example. It is well, I skip it. So this was pure real. So pure imaginary solution, pure real solution is richer. So there is a singular behavior at plus and minus infinity. So I skip it. It is. I would rather now. I would prefer now to talk about complex asymptotics. So asymptotics in sectors. So this is, let us see what the Riemann-Hilbert approach can say about asymptotics in the complex sectors. We start, so to describe those asymptotics, I have to introduce, of course, for many of you, it is very, very, very basic ingredient of complex asymptotics. I call it Boutroux modulus. So it is a function kappa of phi between 0 and pi over 3, which is defined by these complicated but transcendental equations. So this transcendental equation, it is phi, it is kappa. It involves elliptic integrals. K and k, it is k of kappa, it is this. K prime, it is k of kappa prime. E, it is elliptic integrals of the second type. Kind, and E prime it is. So this is a very standard objects of elliptic theory. So this is a system. It can be shown, so this system I Boutroux has a unique, it can be shown that the system has a unique smooth solution. If you normalize this solution as kappa goes to 1 when phi goes to 0 and kappa goes to 0 when phi goes to pi over 3. Okay, so this is some functions of phi. And now, well, maybe I should mention that it looks kind of, well, it looks explicit, exact, but maybe not much conceptual. So of course, from the origin, well, Boutroux himself wrote this type of relation, but isomonodromic origin of this is the following. It is based that for both approaches, WKB and nonlinear series descent, there is the central role is played by this spectral curve. So this is the elliptic curve whose branch points are defined by the following relation. So it is an elementary relation, but this is a relation, this is a Boutroux relation on the periods of this elliptic integral. So this is basically what those relations are, which I saw in the previous slide. And just for people familiar with the nonlinear series descent, of course, this omega is used to construct the so-called G function. So the things which behave as this exponential asymptotics in Riemann-Hilbert problem. So in the analysis, you replace this exponent by this e to the tgz, and this is the first step in the nonlinear series descent analysis to get this asymptotics which I said. Now, theorem. So we have this kappa of phi. Now let's consider generic case. So S2 is, so now it is general complex Painleve. So not imaginary necessarily, not real. So generically S2 is not zero and this combination is not zero. Then the corresponding U behaves like this. It is kind of the square root of x, some combination of this kappa, then elliptic sign. This is a frequency, this is a phase behavior, and this is the phase. This is a phase. This phase is a linear combination of the major periods of elliptic sign, and the coefficients of this is given by explicit formulas through the monodromy data. X goes to infinity, argument X is in 0 pi over 3. Well, you cannot necessarily, so this phi, it is kappa phi. So it is, roughly speaking, you can say that kappa is of argument X. So that is the theorem. That is the theorem. And it is, of course, asymptotic as a uniform. You have to throw away kind of the Swiss cheese domain. You have throw away the poles of this function, and this is a d epsilon, and this is so this is a theorem. This is a theorem, and this is again a piece of history. Of course, this sort of the asymptotic was first suggested by Boutreau, rigorously proved by Joshi and Kruskal. No formula for the phase for these coefficients were given. But not surprising, they did not use monodromy approach. And these formulas for the phases were given later on in Novakshonov, Kapaev, Kitaev works, which were done kind of during this period. So why it is important to have formulas for phases? Why it is important to have formulas for phases? It is because I can now, from this theorem, get for free asymptotic representation in all other 5 sectors. Because this is a simple fact, it can be checked, that of course there is this symmetry of the Painleve equation. You can rotate X, you can simultaneously rotate U, and there is another symmetry. An important thing is that we know that the monodromy data in such convenient parameterization of Painleve functions that we know how this symmetry, what automorphisms on the monodromy manifold this symmetry generate. Very simple. So this symmetry, this is C2L. CD, it is just, so this is written like that. So this is automorphism. It is, of course, can be taken modulus of this relation. And S star, it is this, it is S star of this number G, it is complex conjugate, 4 minus G, again, modulus this relation. So this is why it is so great to have parameterization of this coefficient in terms of monodromy data, because now we immediately extend so on all 5 rays. So for instance, when it is minus pi over 3, 0, it is this, then asymptotics is given again by the similar things, but of course, kappa should be recasted. Kappa bar, it is my basic kappa. Boutreau modulus calculated of minus phi, it taking complex conjugation. And this is a new coefficients for this sector. Of course, you have to assume that again, generic condition that those combination of Stokes multiply is not 0. Okay, I have all similar things for all others, but let me just summarize. So summarize it as a nonlinear Stokes phenomenon. It's probably not what in your community things are called nonlinear Stokes phenomena. This is exactly what I call by that. So it claims, it is a statement that behavior of function U corresponding to the generic choice of monodromy data is this elliptic sign. So this elliptic sign, these parts and these parts are determined just by Boutroux equations, and this is the phase. This is a phase. It is a linear combination of the basic periods. And now I put in each sector what combination should be taken for K prime and what should be taken for K. So that is so this recasting of phases is what we rather call nonlinear Stokes phenomenon. Nonlinear Stokes phenomenon. Of course, again, just like with the previous example of asymptotics of pure imaginary Painleve on the real line, I can kind of exclude S's. So I can treat this as you have phase, you have just phase one phase, and you just recalculate this one phase to the other phases. But this parameterization is, of course, much more symmetric. So it is, of course, you have to remember that your S's are related by this thing. So this is the ultimate answer. Of course, there is extremely interesting question: how to go through this. So we know. So now I want to say that I already described how the solution behaves for pure imaginary case on the real line. But of course, there are answers for any, not necessarily for real line. So for all these rays, the behavior is trigonometric. Sometimes it is tangent, some cosine, sine, square roots. So it is trigonometric. This is elliptic. How you go from this elliptic to this trigonometric behavior. And the phases are so formally, you can see, sometimes you can, of course, people try to do it, and you can see how a sinh becomes usual sign and logarithmic phase, even you can see how it appears, but how all these gamma functions, how this non-trivial formulas for phases appears. So for sometimes I thought that it is, but now I believe it can be done. And I saw recently, very recent papers by Takea, and very recent today, I got today in SolveInt archive paper by Artur Vartanyan, when apparently it is exactly for this problem when the instanton expansions would be very useful. So apparently with this problem, this is where we can come together in a sense. But anyway, so this is a problem is open, and it would be great to get it. So far, what we have about Painleve 2, we have, as I just presented, this generic behavior everywhere and along the line, but the transition itself, so the kind of the genuine nonlinear Stokes phenomena, to see how it is, how it would be great to figure out. Okay, so this is what nonlinear Stokes phenomena, but now I am going to say about quasi-linear Stokes phenomena, which now I begin to approach very close to the things which already also can be done by hyper trans series and resurgent analysis. So this is, I don't know. So this is probably now this I mentioned recent Ivakis work, when he managed to get indeed some sort of instanton conformal block series for complex, and and actually managed to get the elliptic asymptotics from these series. So that's probably when it. But now, but quasi-linear Stokes phenomenon, this is where we already met. So what it means? Look, if it is not generic, if for instance this thing is 0, then of course it is not. There is no elliptic asymptotic here. There is again algebraic asymptotic here, and this is what I'm going to talk now. I believe I still have about maybe 7 minutes, so I will probably to convey the main things. First of all, so we start from the, of course, from the well-known fact that when I balance this part of Painleve equations, I arrive to this formal series solution. So this formal series solution, people usually works with the Painleve 1, which is very, of course, similar, but it's Painleve 2. So we have this formal series solution. Coefficient satisfies recurrence relation. And okay, now, so we have formal series solution. Now, what about the genuine solution? So this is 3 Tranche solutions. This is 3 Tranche solutions, which again were discovered probably by Boutron. But I will present the treatment of this 3 Tranche solution, kind of the Riemann-Hilbert treatment, according to Andrei Karpaev. So it is sort of the tribute to his memory. So this is, and he was the very first who actually calculated all the constant for Tranche solutions. Okay, so what is the claim? The claim is the following: that there are 3 unique solutions. Well, there are more, but I would just talk about U0. So it is when I take S2, S1. This relation between Stokes matrices, which means not only this 0, but also 1 minus S1, S2 is also 0. These 2 are 0. So we cannot write elliptic solution everywhere here, but we have this formal series. So all this formal series works in this big sector. If we take S2. If this relation, so it is now again 1 minus S1 S3 is 0, but 1 plus S2 S3 is also 0. So this is this other part. So now I would have the formal asymptotics, the square root asymptotics over there. So this is this. And finally, the third one, it is when I have this relation between, it is now these combinations are 0. And this is, of course, the asymptotics here. Of course, they are those 2 solutions are related to U1. All this is simple. All this, to establish the existence of this solution, you don't need Isomonodromy-Riemann-Hilbert. And they were known, I believe. Now, what we use, what Andrei used the Riemann-Hilbert, it is to establish this. So this is a quasi-linear Stokes phenomenon. So the difference between U0 and U1, for instance, they would be both kind of live in this part, is this exponentially small, and this is exact constant. So this is exact Stokes parameter for Painleve 2. So there is similar for Painleve 1. I believe Andrei also in his talk talked about it when he talked about Painleve 1. So this is for Painleve 2. And what is important, the asymptotics is on the closed domain. So simultaneously it means that U0, it is, if first it was on 2 pi over 3, but now I can extend the asymptotics to this part of the sector, to the upper part of the sector, to the upper boundary of the sector, and I can write this solution. So this is what I see when I go to the boundary of the sector. And similarly for U1, I can go to the another part of the sector, and I see it here. And everything is explicit, everything is done. And I did not use any resurgent and trans-series arguments. That is a purely from Riemann-Hilbert approach or WKB. The same kind of similar things was done by using WKB by Takea, also for Painleve 1. Now it is three trunkia. Of course, if I consider only this relation and take S2 free, then I would have one parameter family of Painleve equation, which has this power asymptotics in this sector, in smaller sector, open. And now, again, another manifestation of nonlinear Stokes phenomenon. This trunkia solution I can extend to 2 pi over 3, and it would produce this exponential term. I will see this exponential term, and this S1 plus S2. So this is S1 is known, and S2 is free parameter. And on the other, I can go to the other direction and get this parameter again. S2 is known, S3 is known, S2 is free parameter. So we arrive to this most common manifestation of quasi-linear Stokes phenomenon. I have trunkia solution, which has this asymptotic behavior on this semi-closed sector with C plus coefficients of the exponent, and in this semi-closed sector with C minus. And I know the difference. C plus minus C minus is given by this explicit formula, explicit number. So that is the kind of demonstration of what can be done with the Isomonodromy-Riemann-Hilbert approach. Of course, interesting member of trunkia family is the situation when S2 is 0. When S2 is 0, you remember when S2 is 0, it means that we have one more free sector, this one. So we have algebraic behavior here, and we have also, well, exponential behavior there. So then it would mean that we would have yes. So it is, yeah. So this is a Hastings-MacLeod solution. So I have behavior at this sector like that, at this sector like this, and also I can extend this behavior for Hastings-MacLeod to the low boundary of this sector, to the upper boundary of this sector, and I know exactly those coefficients. And also I know what is going on with my Hastings-MacLeod everywhere else. So what is going on in this sector? It is this elliptic function. And I can, of course, figure out about its poles. And what is going in this sector? It is this elliptic function. Again, everything is explicit. Well, Victor Novakshonov, so in particular, it would mean that in this sector, there will be poles. There will be the lattice of poles. And he actually made a very nice numerical comparison of these formulas. They were very good. They give very good. So he used it as, again, what Novakshonov done, it is also very close to the topics of this program, because he used PD approximation to analyze all these poles. And this is picture what he get from his numerical analysis. And so as a result, he come up with a conjecture he come up with this conjecture that those sectors, when we have exponential and square root asymptotics, they are free of poles. It was proven in 2015 by Huang, He-Hu, and Shang. And actually, even before, for this sector, it was proven by Bertalan. And this work, actually, it kind of uses both techniques, trans-series and results from this isomonodromy analysis. So there is a hope that we will be kind of together eventually. So I have to finish. So let me just make historical remark. So of course there are other. So what I presented, it is what can be done with the help of Riemann-Hilbert asymonodromy approach. So of course there are other important works on truncated solution and poles of Painleve. First of all, of course, Boutreau. Then this group, of course, starting from Aviti, they've done remarkable works on location of the first poles, alternative description of quasi-linear Stokes phenomena. So here, Kostin, Tanvier, and Huang, they indeed, well, for Painleve 1, they indeed produce the same constant what Andrei Kapaev and Takei calculated using the just without any use of isomonodromy technique. And what, of course, most importantly, they proved the Brovin conjecture. This is what we cannot do, at least so far. Then I want to mention Joshim and Kitaev, who again studied the position of the first pole and some monotonic properties of three-truncated solution. With Masoka, Nalini, they analyzed, they proved the existence of truncated solution for the higher hierarchy. Then very beautiful works of Fornberg and Weidmann about numerical study of poles. Davida Mazaera, poles of trigonometric relation between the poles of three-truncated solution and anharmonic oscillators. Now it is very relevant. So his work, he started it some time ago, but he is continuous, and it is of course very relevant now in connections to some very recent works on accessory parameters in anharmonic oscillator, Mathieu equation, and Painleve equations, and also in more general ODE IM correspondence. So this is now a hot topic. Clarkson and Mansfield. So this is a special patterns in the pole structure should be mentioned of the rational solution. So it is this observation of this kind of the also very remarkable pictures generated a lot of activity recently in random matrices and in extremely interesting in connections with the so-called Shapiro-Tatar conjecture about the spectrum of quartic potential. Okay, I should stop there. Thank you.
Okay. Yeah, I'd like to thank Alexander for such a clear and beautiful talk about the isomonodromic deformation method and Painleve equations. But I'd like to open it up to anyone who'd like to ask questions now. Has anybody got a question? Just turn on your video or your sound if you want to ask a question. Tamara?
Oh, hi, Alexander. Many thank you for this very nice overview. No, I just want to add maybe a reference of the last work. Before the last work of Andrei Kapaev on this three truncated for the P12.
Mm-hmm.
So we studied two families of three truncated solutions.
Mm-hmm.
That paper, yeah, it's the last work of Andrei, I think.
Yes, thank you, Tamara. Of course, yeah, I should have mentioned about that. But there are so many things which I should have mentioned.
No, it's great. I mean, you mentioned.
This is why the program kind of exists. So it is indeed, and it is. I miss several names, of course, also. Especially in the non-isomonodromic part, because I don't also, so I just mentioned mostly the people whose works I know and appreciate, but there are many others, of course. But still, my main message probably is that it is kind of about the time to find common ground, and probably now I begin to think that this instanton construction is, you see, there is a, okay, that's simply, so there is a, No. There is a mechanism how instanton appears in terms from Riemann-Hilbert problem. So I don't want to take your time. I just 2 words. So this is a very simplified Riemann-Hilbert problem for Ablovis-Sigur family. And so to solve equation, you eventually end up with this representation of solution in terms of where this is a jump matrix and rho is a solution of the integral equation, which corresponds to this Riemann-Hilbert problem, singular integral equation. And this singular integral equation you can solve by Neumann, because it is okay. The jump matrix is very small. You just have a Neumann series, and of course, this Neumann series through this formula generates the instanton series for Painleve. So this is a convergent series.
Can I ask? Sorry, Alexander. The formula, the integral formula, is that what you would call the non-abelian contour integral?
Yes, exactly.
Yeah.
And there are reasons for that, because you can really consider some triangular reduction on this setting, and you arrive to, of course, to ARA equation would becomes exactly the contour integral for ARA equation. So this is exactly because it is not, so the origin, this is a non-linearity, means that you don't have something like without this, some kind of the explicit contour integral. You just would have only one series, but you have this. You have this, which has this Neumann series, and so it is you would get instantons. It is, by the way, it is very what I get this, it is very okay. Anyway, so this is so it is the Neumann series, and I believe I already mentioned this work which I come across just recently. I did not have time to read carefully. Takes, where he kind of managed to get elliptic functions from instanton, which is not very surprising because it is indeed instantons. It is sort of the Fourier expansion, and when you come to the Stokes line, and so it can be expected to be sum up to the theta functions. So I think that, and probably this is where we can, because one of the really challenging, I would say one of the really challenging unsolved problems, it is kind of to describe how some uniform asymptotics, some critical asymptotics around this race. So how you get from trigonometric to elliptic, from elliptic to trigonometric, from one elliptic in one sector to another elliptic. So that is a great problem. That is what, and this is where I'm sure all the techniques should come together. So, if you have tough problem, you have to solve it using the all means available. And yes, and I'm very kind of optimistic. So that's it's so, because we already got experience. So our community already got experience of this critical asymptotics. Tamara would confirm it that in random matrices. So we now can, or for instance, relate Hastings-MacLeod solution with Ablovis-Sigur. So we have now some experience in this, and some structures as instanton sums also appears. And I also want to look at this big paper by Artur Vartanyan, which I just saw today. I just said so today. It is 101 pages, of course. But it is when he also claims that it is an abstract. I read abstract when he said that he also reproduced instanton expansions. So instanton expansions, Pade approximation. So all this should be somehow.
Any more questions, please? Anyone?
I have a curiosity.
Yes.
Rather. First, can you send the reference for the Takei paper?
For what?
The Takei paper.
Ah, Takei paper. Brrr. Yeah, okay. I don't have it with me.
Because I tried finding it and I can't find it.
You see what I found. I also actually I cannot send it to you. Maybe we have to ask him, because indeed I Google. I found reference, but I could not read it. So yes, it's only kind of announcement, only abstract.
So this is I'm a bit curious about the last statement, that when we start from absolute Ségur, you're getting a series expansion as a natural consequence of some contour integrals. Is that correct?
Say it again. How do you say?
Starting from the absolute Ségur.
Yeah.
Just from the contour integral over each of the contours.
Yeah.
The claim is that you're getting the series expansion.
Yeah. Yes. I believe it is somewhere in your work should be also hidden, because so what I get here, it is very rough. It is very rude. I just look at the original problem. Jump matrix is small.
Right.
Yeah, but it is kind of small without power smallness. So it is just this L infinity.
Mm-hmm.
But of course, you have to be more subtle. You have to first kind of solve this triangular problem on the upper branch and on the lower branch,
mm-hmm.
and then you would get here also you would get here also some power decay,
mm-hmm.
and then you would get so considering the Neumann problem of this deformed Riemann-Hilbert problem, you would get instantons, kind of genuine instanton.
Mm-hmm. Okay.
And somehow I think that this, of course, should be also related, because it's also related to determinant formulas which you have.
Yeah.
So that is so I think that now we have several most interesting developments kind of coming together. They really intersect.
Mm-hmm.
To say nothing about all the successor parameters and kind of no, that's it is a good time to do asymptotics.
Any more questions from the floor, from the audience?
Yes, I would like to ask a question. I don't know if it is well defined, but anyway, so suppose we have a generic solution of P2.
Mm-hmm.
So is it possible to design some kind of scattering problem for KdV or MKdV, which would produce this solution as a similarity reduction?
Mm-hmm. Okay. I've been working with Painleve as KdV all my life, and I cannot answer it once. It is very natural of ask. Well, you certainly you should be able, Oleg, because construction, but you have to start from some not, of course, rapidly decreasing or even periodic solution. You can start from some. So you can consider solution of KdV parameterized by function, some functionally parameterized solution of KdV, and this function would be just the functions which parameterizes jump matrices. So you can set the Riemann-Hilbert problem similar to Painleve 2, but your S's are not constant, but they are depends on lambda. Then you would not have any more differential equation with respect to lambda. But you can also introduce time. You can write not for 3i lambda q plus ix lambda, but you can write t. Of course, you can write t in Painleve too, but it is immediately factored out because jump matrices don't depend on lambda. So you just make self-similar reduction and you are done. But if you keep t, you keep x, and you make s depending on lambda, you get some class of solution of KdV. You get some class of solution of KdV. And now if you consider, and your s of lambda can be, you know, kind of formally, they can be any, you see. Just to take care to problem well set, and that's it. And then you do self-similar reduction in this setting. And you would arrive to generic. The other things, you see, the other things is that when we talked about KdV, we always talk about real x and real time. So you would get generic Painleve, but for real x's, for real. So not on the complex domain. But in principle, yeah, you get it. But
you would have singularities, wouldn't you? At
yes,
time zero and so on, because the scaling variables are like x on t to the 2/3 and and so on. So it would be blowing up definitely.
Yeah, it would be yes. Everything would be local. Everything would
be local. It would be a very singular solution. Yeah.
So this class of the solution would be very difficult. You see, would be very difficult to describe this class of the KdV solution in some, you know, intrinsic terms. So what initial data would generate? So this extremely difficult, would be very difficult to answer.
Yeah, some kind of blow up solutions.
Very difficult to answer.
But maybe if you looked at Tri-Tronqué, though, you could try to exclude poles at least in some part, you know, for maybe for positive time or something like that. But perhaps you could. But it would definitely be blowing up at time zero, and it would be blowing up wherever the
Tri-Tronqué, of course, appears, you know, all these works of Miller and Tovis, Tamara has worked, so the Tri-Tronqué appears exactly in this quasi-classical analysis of NLS, KdV, so this is, and they appears very, in a very kind of profound way, so.
Yeah.
Kind of their poles, you know. I believe the logo of your program is exactly that. The logo of the program, you know, yes, when you have this water and some pikes on the water. It is exactly Tri-Tronqué solution, I believe, in the form of NLS, or maybe KdV.
Thanks.
Thank you.
Okay. So I was just going to say about these non-abelian contour integrals. So because you were mentioning that the asymptotics formulae for the Painleve equations doesn't look that different from you know, linear special function asymptotics in a sense, which are given by normal contour integral representation. So could you say that it's the non-abelian contour integral which is somehow the origin of this simplicity in a sense? Is that perhaps?
You know, I don't think so.
No.
So yeah, so this is the origin of this simplicity is that we are working with Painleve equation. It is because it is 2x2 problem.
Yes, true.
It is, and because it is only, you know, all this, this important is matrix dimension, and important is the structure of the essential singularity.
Mm-hmm.
It is cubic, it is fourth power, it is maybe fifth power for Painleve 1 in one form.
Mm-hmm.
And so when you go to the model problem, you simplify everything, but it is still 2 by 2.
Yeah.
And the model problem, it is usually the turning point, is a simple turning point or double turning point. Again, because 2 by 2 you only have this, because of the cubic fourth power, you don't have many of them. More higher turning points, and so you will arrive this Riemann-Hilbert problem, and they will be also non-commutative, by the way.
Mm-hmm.
This is a strange thing. So you can formulate this non-commutative Riemann-Hilbert problem still, because the essential singularity is not too high.
Mm-hmm.
For instance, when essential singularity e to the lambda squared, then it can be solved in parabolic cylinder function.
Mm-hmm.
If it becomes lambda cube, it cannot. So model problems for the no more than double turning point, they always solvable explicitly in hypergeometric functions. If you have the higher hierarchy, if you have matrix dimension higher, then your model problems would not be, you should not expect that your model problem would be solved explicitly. For instance, in the works of Oleg and his collaborators, when they write, these Fredholm determinant representations for the general, say, Fuchsian system, for the higher rank, okay, so the kernels are given in terms of some model problem, already no parameters in the no x in them. So it is sort of special function, but it is special function which is not given in terms of counter integrals, which is given in terms of some model Riemann-Hilbert problem, model differential equation, which don't have any x's anymore, so they all factor it out. It's good. But you can, so, and if you have, again, in random matrix is the same. If you have the generating point, critical point of the higher degree, even if you have 2 by 2 problem, you still you cannot do much of it.
Right. Thank you. Okay.
Yeah. So that's what. So again, I have to apologize because it is such a diverse and hard area. I definitely have not mentioned many many participants in the recent developments, and many part of it which I should, but no.
I could see Adri has appeared, and maybe he's telling us we should should we wrap it up if there are no more questions?
No, at least the official discussion that is being recorded. We can continue afterwards.
Stop recording, yeah. Okay, well, it just remains for me to thank Alexander again for such a full talk. Okay.
And thank you again for having me. So that's,
Yeah.
So we can finish now the official recording then of this.